At first glance, the world of mechanics might seem dominated by tools, grease, and the roar of engines. The image of a mechanic, hands covered in oil and grime, working tirelessly under the hood of a car, is a familiar one. It's a world where physical labor and technical skill come together to keep our vehicles running smoothly. However, beneath the surface lies a hidden language that governs every repair, every adjustment, and every modification mathematics. This language is not immediately visible, but it is the foundation upon which the entire field of mechanics is built. Every tool, every measurement, and every calculation is rooted in mathematical principles. From the simplest oil change to the most complex engine rebuild, mechanics rely on mathematical principles to diagnose problems, calculate measurements, and ensure everything works in perfect harmony. For instance, when performing an oil change, a mechanic must know the exact amount of oil required, which involves understanding volume measurements and conversions. This essay delves into the fascinating world of mechanics, revealing how math is not just a tool, but an indispensable language in their daily work. It explores the various ways in which mathematical concepts are applied, from basic arithmetic to complex algebra and geometry, highlighting the critical role they play in ensuring the functionality and safety of vehicles. Imagine a mechanic diagnosing a car problem. The process begins with a careful analysis of the symptoms. Much like a doctor diagnosing a patient, the mechanic listens to the engine, observes its behavior, and uses diagnostic tools to gather data. The engine sputters and coughs. These sounds are clues that help the mechanic narrow down the potential issues. Each sound, each vibration, and each irregularity is a piece of the puzzle. Is it a fuel issue? A spark plug problem? The mechanic must consider all possibilities, using their knowledge and experience to systematically eliminate potential causes. This process involves a series of calculations and measurements, each one bringing them closer to the solution. A mechanic uses their knowledge of engine timing, measured in degrees of rotation, to pinpoint the issue. Engine timing is crucial for the proper functioning of the engine, and even a small deviation can cause significant problems. By understanding the precise timing required, the mechanic can make the necessary adjustments to ensure optimal performance. This is just one example of how math underpins the mechanic's craft. From calculating the correct torque for tightening bolts to determining the appropriate gear ratios for different driving conditions, math is an essential tool in the mechanic's toolkit. Without a solid grasp of mathematical concepts, a mechanic would be lost in a labyrinth of gears, wires, and engine components. The ability to understand and apply these concepts is what sets skilled mechanics apart, enabling them to tackle even the most challenging repairs with confidence. Math provides the roadmap, guiding them through the intricate workings of machines. It allows them to visualize the relationships between different components, predict the outcomes of their actions, and make informed decisions that ensure the safety and reliability of the vehicles they work on. Whether it's calculating torque, measuring engine displacement, or understanding gear ratios, math empowers mechanics to make informed decisions and keep vehicles running smoothly. By mastering these mathematical principles, mechanics can achieve a level of precision and efficiency that is essential in today's fast-paced, technology-driven world. So the next time you see a mechanic at work, remember that behind every turn of the wrench and every adjustment made, there is a complex web of mathematical knowledge at play, ensuring that your vehicle operates at its best. One of the first things a budding mechanic learns is that the world of measurements is divided. This division isn't just a minor inconvenience, it shapes the very foundation of how they approach their work. Understanding both systems is not just a skill, but a necessity in the field. On one hand, there's the metric system, a globally embraced system based on multiples of 10. This system is known for its simplicity and ease of conversion, making it a favorite in scientific and engineering communities worldwide. The metric system uses units like meters, liters, and grams, which are all interrelated by factors of 10. On the other hand, there's the American system, also known as the imperial system, which relies on units like inches, feet, and pounds. This system has its roots in historical measurements and is still widely used in the United States. The imperial system can be more complex due to its lack of a consistent base, requiring more memorization of conversion factors. Mechanics often find themselves navigating both systems, seamlessly switching between millimeters and inches, grams and ounces. This duality is a testament to their versatility and adaptability. They must be proficient in both systems to handle the diverse range of vehicles and machinery that come their way. For instance, a mechanic might grab a 13mm socket wrench to loosen a bolt, then switch to a half-inch wrench for the next task. This ability to fluidly transition between tools and measurements is a hallmark of their expertise. This constant conversion between metric and American units requires a strong foundation in basic arithmetic and an understanding of the relationship between the two systems. Mechanics often use calculators and conversion charts to ensure accuracy, but over time, many develop an intuitive sense for these conversions. Knowing when to use each system is crucial. It's not just about having the right tools, but also about understanding the specifications and requirements of the task at hand. This knowledge can prevent mistakes and ensure that repairs and maintenance are performed to the highest standards. Engine components, often manufactured to precise metric specifications, demand the accuracy of millimeters. These parts are designed with exact tolerances, and using the correct measurements is essential for the engine's performance and longevity. On the other hand, tasks like measuring tire pressure might use pounds per square inch, or PSI. This unit is commonly used in the automotive industry in the United States and is crucial for ensuring the safety and efficiency of the vehicle. This constant interplay between systems underscores the adaptability and mathematical fluency required of a successful mechanic. They must be able to think on their feet, make quick decisions, and apply their knowledge in practical, real-world situations. This dual system expertise not only enhances their skill set, but also broadens their opportunities in the global market, making them invaluable in an increasingly interconnected world. While the metric system simplifies measurements with decimals, the American system often relies on fractions, especially when dealing with nuts and bolts. Mechanics encounter fractions constantly, using them to identify the correct wrench size, determine thread pitch, and ensure parts fit together precisely. For example, a mechanic might need a 3/8-inch wrench to loosen a bolt on the suspension system. This seemingly simple task requires an understanding of fractions. The mechanic must know that 3/8 is smaller than 1/2, but larger than 1/4, allowing them to select the correct tool from their arsenal. Beyond basic identification, mechanics use fractions to perform calculations. Imagine needing to drill a hole exactly halfway between 2 points on a metal plate. This requires dividing the distance by 2, a simple yet essential application of fractions. Mastering fractions is not just about memorizing numbers. It's about understanding the relationships between them, a skill crucial for accurate measurements and precise work. Section 4. Torque, tightening the relationship between force and distance. Imagine tightening a bolt. You might think it's a simple task, but there's a lot more to it than just turning a wrench. How much force is too much? Applying excessive force can lead to damaging consequences. Conversely, how much is not enough? Using too little force can be equally problematic. This is where the concept of torque comes into play. Torque is the measure of the twisting force applied to an object, and it is crucial in ensuring that bolts are tightened correctly. Torque, measured in pound-feet or newton-meters, represents the twisting force applied to an object. It is a fundamental concept in mechanics and engineering. Mechanics use torque wrenches, specialized tools that click when a specific torque is reached, to ensure bolts are tightened to the correct specifications. This click is an audible and tactile signal that the desired torque has been achieved. Understanding torque is essential for preventing damage to delicate components. Delicate parts require precise torque to avoid damage. Over-tightening a bolt can strip the threads or even crack the part, leading to costly repairs and potential safety hazards. On the other hand, under-tightening can lead to dangerous loosening over time, which can compromise the integrity of the entire assembly. To avoid these issues, mechanics use torque charts and formulas to determine the correct torque for each bolt. These charts take into account factors like thread size, material, and application, ensuring that each bolt is tightened to the appropriate specification. For instance, a cylinder head bolt, responsible for holding the engine together, requires a significantly higher torque than a bolt securing a plastic cover. The difference in torque requirements is due to the varying rolls and stresses each bolt will encounter. Mechanics use their knowledge of torque to apply the right amount of force, ensuring a secure and long-lasting connection. This expertise is vital in maintaining the performance and safety of the vehicle. This precise application of force, guided by mathematical principles, is crucial for maintaining the integrity and safety of a vehicle. By understanding and applying the correct torque, mechanics ensure that every component functions as intended, providing reliability and peace of mind to the vehicle owner. Section 5. Engine displacement, measuring the heart of a machine. One of the defining characteristics of an engine is its displacement. Engine displacement, often measured in liters or cubic centimeters, represents the total volume swept by all the pistons inside the engine cylinders. This measurement provides a general indication of an engine's power potential. Larger displacement often translates to more power. To calculate engine displacement, mechanics use a formula that involves the cylinder bore, the piston stroke, and the number of cylinders. This calculation requires a basic understanding of geometry, specifically the formula for the volume of a cylinder. For example, a 4-cylinder engine with a bore of 84 millimeters and a stroke of 90 millimeters has a displacement of approximately 2 liters. This figure is essential for mechanics when diagnosing engine problems, ordering replacement parts, or even comparing the performance characteristics of different vehicles. Understanding engine displacement is akin to understanding the size and capacity of the engine's heart.